This is the third part of our discussion on analytic functions. So far, we have defined what are analytic functions, and we also discussed some examples. And later, we and discussed some conditions that we can use to check whether a given function is analytic or not. Okay, so this includes very simple criteria. For example, we used the fact that if f and g are differentiable, then their sum is also differentiable, and using this simple fact, we can determine whether the sum of two analytic function is analytic or not, and similarly their product, and similarly their quotient. And using these facts, we were able to determine whether or at what points a given rational function is analytic. And similarly, we used sufficient condition for differentiability to check whether a given function is analytic at a point or not. Now, let's recall ourselves what is an analytic function. So, a function is analytic at a point z0 provided there exists some non-zero positive real number epsilon greater than 0, such that in this open disk with center z0 and radius epsilon, this derivative of f exists at each and every point inside this epsilon neighborhood of z0. Okay, so not only the function is differentiable at the point, but at each and every point in the epsilon neighborhood of z0. Okay, now moving on to properties of analytic functions. One of the simple properties of analytic function is if the derivative of a complex valued function is 0 everywhere in a domain D, then the function must be constant. Now, there is no word analytic in this statement, but since the derivative exists because it is 0, okay, so it is assumed that the derivative is 0, so it must exist first. So that's why the derivative exists everywhere in the domain D. Now, what is a domain D? It's a connected open set. Okay, so what is a domain? It is connected open set. Okay, so it is something like this. Okay, so it is connected, the boundary is not included, so it is open. And if the derivative exists at each and every point in an open set, then we discussed it in our earlier discussion that this function must be analytic in the whole domain D. Okay, so f of z is analytic on throughout D. Okay, so it is analytic at each and every point in this domain D. Now, the given assumption is that the derivative of this function is 0 everywhere or at each and every point in this domain D. And what do we need to prove? That this function must be constant. Okay. Now, this is a very simple property of real valued functions. Okay, so we know that. Okay, so let's discuss this thing in the real valued function case. Okay, so if y is equal to h of x is a real valued function. Okay, and we know that if h prime x is 0, then it's a very simple exercise to check that this implies h of x is basically a constant. But in the complex valued case, it's relatively non-trivial as compared to the real valued case to prove that if the derivative is 0, then the function must be constant. Okay. Now, let's see how to prove this fact. Now, the point is if we have components, okay, so let the function f of z, which is basically equal to f of x plus iota y, if it is given in its component form, so the first component or the real component is u and the imaginary part is v of xy. Okay. Now the function is analytic. In other words, it is differentiable, and we know that if f is differentiable, okay, so if f of z is differentiable, at a point, then the derivative is given by ux plus iota vx, differentiating both components. Now also the function is once again analytic, so it is differentiable, so it must satisfy Cauchy-Riemann equations. Okay, so once again f of z satisfy, or the components of this function satisfy Cauchy-Riemann equations. So in other words, ux must be equal to vy, and since ux is 0, okay, so we will move on to this assumption later, and now the next thing is uy must be equal to minus vx. Now what is given? So the given part is f prime z is 0. So this implies that ux plus iota vx is 0, and definitely this implies ux is 0 and vx is 0. So this is the given part, and using these Cauchy-Riemann equations, let's call them set of equations 1. So this set of equation 1 implies that vy, which is in fact equal to ux, must also be 0, and similarly this vx, which is basically equal to uy, so this must also be 0. So in other words, partial derivative of u with respect to x is 0, partial derivative of u with respect to y is 0, partial derivative of v with respect to x is 0, and partial derivative of v with respect to y is 0. So all the first order partial derivatives of u and v are 0. Now this is first step. Okay, so far what we have proved. Okay, so if f of z is equal to u plus iota v, then this implies ux is equal to uy is equal to 0, and vx is equal to vy is equal to 0. Now we want to show that, okay, so what do we want to show? So we want to show that this function f of z is constant. So in other words, what do we want to show? U is constant. Okay, so this is only possible if the real component is constant and v is constant. Okay, so we will, for example, focus on the component u, and the strategy for showing that v is constant is the same. Okay, so in our next second step, we will show that, okay, so aim is to show that u is constant. And of course, when we say that u is constant, it means in the domain D. In domain D. Okay, so now u is a function of two variables. It's a real valued function. U, if we want to show that it is a constant function, we want to show that its value remains the same at each and every point in the domain. So for example, if I choose 2 points, let's call them p and p prime, then the value of the function u is the same at both points p and p prime. Okay, so now the strategy that we are going to follow to show this thing is very simple. Okay, so if we choose a line joining these 2 points, okay, and if we restrict the function u on this one line, and let's call the parameter of this line to be s. So when we say parameter, it means when we vary s, then it gives us points of this line segment. Okay, so it's a very simple exercise of vector calculus to find the equation of a line joining, in fact, the line segment joining p and p prime, and the local parameter is s. Okay, so if we restrict this function u on this line segment, and if we are able to show that the restriction function has derivative equal to 0, then it means that the function u does not vary on this line. Okay, so if the derivative of the function when restricted to this line is 0, so it means the value of the function u at point P and the value of the function at point P prime are the same. Okay, because the derivative of the function is 0 on this line, so the functional value does not change on this line segment. So that's why its value at P and P prime remains the same. So that's the kind of idea. Now, how do we restrict this u on this line segment and then find its derivative? Now, we are going to use the concept of directional derivative here. So what is a directional derivative? So if I am standing at a point P, and if I want to calculate the rate of change of u, but now since we are in 2 dimensions, the domain of u is a 2-dimensional subset of the plane. So I need to give a direction in which I want to move. Okay, so I want to find the derivative of u in some certain directions. Okay, so without any direction, the derivative in this case does not make any sense. So let u is that direction, such that when we move from P in the direction u, then we reach at point P prime. So this is the line segment L. And if I want to calculate the directional derivative along this line, then we have a very simple formula. Okay, so remember, S is the local parameter. Okay, so what is du by ds? So once again, when we are saying du by ds, it means we have restricted the function u on this line segment, and S is the local parameter. So that's why u is a function of one variable now. And what is the variable? S. Okay, so that's why we can talk about the ordinary derivative of u with respect to S. So this is in fact equal to gradient of u dot this unit vector u. Okay, so now the point is, what is the gradient of u? So the gradient of u, we know that what is gradient of u? It is in fact uxi plus uyj. Okay, and let's assume, for example, so this u is different from this u is the unit vector, and this u is the component of f. Okay, so now let's assume for a moment that this u is equal to let's say c1 I plus c2 j. So I'm taking them to be c1 c2 not to, so that they don't get confused with this ux and uy. Okay, now let's take the dot product of this thing. So this becomes c1 ux plus c2 uy. And of course, when we are saying ux, it means we evaluate the partial derivative of u at the points of this line. Okay, now the point is, what is ux? Okay, so in this entire domain D, ux is 0. And similarly, what is uy? So uy is 0 on this entire domain. Okay, so this is 0 in domain D. So what does it mean? The du by ds is 0 on this entire line segment. And if it is 0 on this entire line segment, then its value does not change when we move from P to P prime. So this implies, okay, so this implies that u is constant on this line L. So it's a very simple implication that value of u at P and P prime is same. So this is the second step of our proof. Now let's see how this observation will help us in proving that this u is in fact constant throughout this domain D. Now the point is, this D is open and connected. So connected means if I choose a point, let's say this is the point P1, and if I choose any other point, let's say this is the point P2, then the connectedness implies that there exists finite sequence of line segments that will join the point P1 to P2. Okay, so let P1 and P2 be 2 points of the domain. Since D is connected, so this implies, so there exists a sequence of line segments. Okay, so let's call that sequence to be, so this is a very particular example, but in general, so there are only 3 line segments, but in general there will be line segment, let's say n line segments joining points P1 and P2. Now we have proved that u is constant at each and every line segment, and if it is constant at on this line segment, and the value of P1 and let's say the middle point Q1 is the same, okay, now on the line segment L2, the value of u, once again the rate of change is 0, so the value of u at point Q1 is the same as at point Q2. Okay, and similarly, since du by ds is 0 on this line segment L3, and the value of u at point Q2 and point P2 is the same, so that's why the value of u at point P1 and P2 is the same. Okay, so using previous observation, we can say that the value of u at point P1 is the same as the value of u at point P, and this clearly implies that u is constant. And the similar argument proves that v is constant. So similarly, v is constant. So this implies our function f of z, which is equal to u plus iota v, is constant. So it's a relatively difficult task in the complex valued case, but still we are able to show that if the derivative is 0 in a domain D, then the function is in fact a constant function. Now let's consider a very particular example where our previously proved result is going to be useful to show that some function is constant. Okay, so in this particular scenario, we have given a function and it is analytic. Also, the conjugate function, in which we just replace iota with minus iota, so this conjugate function is also analytic. So both are analytic functions, and we need to show that this function f of z is constant throughout this domain T. So if f and its conjugate are both analytic, then this is only possible when this function is constant. In other words, it implies that the function is constant. Okay, so what is given? The function and its conjugate both are analytic. And what do we want to show? So we want to show that the function is constant. Now, since this conjugate function is analytic, so it must satisfy the Cauchy-Riemann equations. So in other words, if we assume that the real part is capital U of xy and this imaginary part is capital V of xy. Okay, so this implies that capital Ux, the partial derivative of this capital U with respect to x, must be equal to the partial derivative of this capital V with respect to y. And similarly, the second Cauchy-Riemann equation says that the partial derivative of this capital U with respect to y must be equal to the partial derivative of capital V with respect to x, but with a negative sign. Okay. Now, similarly, the function f of z is analytic, so it must also satisfy the Cauchy-Riemann equations. So in this case, ux must be equal to vy and uy must be equal to minus ux. Okay, so let's see the consequences of this set of equations now. Okay, but remember, capital V is in fact minus V, because if we just compare the real and imaginary parts with u minus iota v, so capital V is in fact minus V. So if so happens, then the partial derivative Vx must be equal to minus Vx, and similarly the partial derivative Vy must be equal to minus small Vy. So what are the consequences of this now? So starting from small ux, so the partial derivative of this small u with respect to x must be equal to Vy. Okay, so we know this thing. Now we also know that this Vy is in fact equal to minus capital Vy. Okay, so that's why this must be equal to minus capital Vy. Okay, so and from here, okay, so now going to the equations relating these capital V's and capital U's. So minus Vy must be equal to minus Ux. Okay, so now we are using this. Okay, so and hence we have this, and since capital U and small u, they are equal, so that's why Ux must be equal to capital Ux must be equal to small ux. So that's why we have this is equal to minus Ux. So what do we get? So this, we started from this small ux and ended up at minus small ux. So this implies Ux must be equal to minus Ux. Okay, so this implies Ux is 0. And similarly, we can show that this Uy is equal to minus Uy using once again the same set of equations, and hence Uy is 0. Okay, so this implies, okay, so similarly we can show that Vx is 0. So what do we get now? So Ux is 0 and Vx is 0, and we also know that f prime z, if it is analytic, then it is equal to Ux plus iota Vx. So this is equal to 0. And using the previous result where we proved that if the derivative is 0, then this implies f of z is constant. So hence we have proved that if function and its conjugate are both analytic, then the function is in fact constant. So in this part we discussed some properties of analytic functions, and we also extended a very simple rule from real analysis to the complex analysis. So if the derivative of a real valued function is 0, then the function is constant. Okay, so real valued in one variable. And now we also know that it is also valid in the complex analysis case. In the complex valued function case, if the derivative of a function is 0 in a domain D, then the function must be constant in that domain D. We also discussed some consequences of this result.